I'd like to ask you a question. What's the greatest enemy humanity has ever had to face? Itself? Not even close. While wars have certainly been destructive and been critical in shaping history, those death counts are nothing compared to those of another enemy, disease. While there have been a few standout examples, whether in lethality or in their spread, one of the most ancient and the most dangerous that still plagues us today is malaria. From fossil evidence dating back over 30 million years to references in ancient Egyptian, Mesopotamian, Greek, Roman, and Chinese records, malaria has been a constant presence in world history since the beginning, and it has been deadly. To give you an idea, estimates from researchers like Professor Brian Farragher from the Liverpool School of Tropical Medicine, as well as a paper published in Clinical Microbiology Reviews, have looked into this. Their data suggests that the total number of deaths from malaria since antiquity has been around 4 to 5%. That's not deaths annually, that's deaths across all of human history. To put that into perspective, it's been estimated that about 100 billion humans have lived and died since our time on Earth began. This would mean that around 4 to 5 billion people have died of a single disease. That's about 40 to 60% of the current world population in 2025. There is not a single war that even comes close, nor do any other diseases match those numbers. But you may have also heard another often repeated figure, that since the Stone Age, half of all humans were killed by malaria. Now, there's no strong evidence to support this claim, and the true figure could be potentially somewhere between the two, but either way, malaria has remained one of the most dangerous and feared diseases throughout history, and every year, millions still get sick, and hundreds of thousands still die, yet we might be close to seeing its end. But to explain why, we need to understand something first. What even is malaria? In a nutshell, malaria is a disease spread by mosquito bites, with symptoms including fever, chills, fatigue, headaches, coughing, joint pain, jaundice, nausea, among many others. And in probably the most eye-opening aspect of the disease, it's not transmissible between humans. Even blood-to-blood contact rarely, if ever, will pass it on. The only way for malaria to spread is through feeding by infected mosquitoes. But mosquitoes aren't the cause of malaria. This is Plasmodium. It's not a virus or a bacteria, it's a group of parasitic protozoa. There are over 200 different species of this microorganism, with those that cause malaria divided into 4 main groups: reptilian, avian, mammalian, and primate. To be clear, most Plasmodium species don't infect humans, and most of those that do are completely asymptomatic. But malaria is caused by 5 different species, all of whom vary in method but operate toward the same end. As with many parasites, they require a host species for them to complete their life cycle, and this is where the disease comes in. The infective form of the parasite, called sporozoites, are transmitted by mosquitoes to the host. In humans, these travel through the bloodstream until they reach their desired destination, the liver. Here, after infecting the liver cells, they mature into their second form, the schizonts. Who comes up with these names, I swear? This marks the incubation period of the disease, where the schizonts start dividing within the liver. This varies depending on the Plasmodium species, but the average is around 7 to 30 days, although some can lay dormant for months, years, or even longer. It's during this period of time that the schizonts are reproducing asexually through a process called schizogony. Their goal for targeting the liver in particular is a special resource, aquaporin 3. This is a protein that normally helps our cells transport water and glycerol across cell membranes. But while in the liver, the schizonts hijack this protein in order to collect resources for the next part of this process. Another crucial part is the production of hemozoin, a biocrystal that blood-feeding parasites produce as part of their infection plan. Remember this, it'll be important later. And it's while hiding in the liver that the schizonts are producing the next stage of the infection, merozoites. The schizonts not only produce these types of cells, sometimes in elaborate patterns, but in protective structures called vacuoles that are filled with hemozoin. These are then released directly into the bloodstream, where they begin to seek out their next target, red blood cells. And in a cunning bit of strategy, the vacuole protects the parasites from being detected by the immune cells, while the hemozoin serves as a protection against free heme in the blood. Heme is one of the components of hemoglobin, and free heme can be highly toxic. This is where the infection officially progresses into malaria, as the Merozoites begin invading red blood cells and starting their own cycle of division. What differentiates this from schizogony is that the Merozoites produce the reproductive form of Plasmodium, the Gameozoites. At this stage of infection, the amount of Plasmodium cells within the body can be anywhere from 10 million to 10 trillion per milliliter of blood. And just when you think it can't get more twisted, at this stage of the infection, the parasite actually changes the way your body smells. Your sweat, breath, and body odor are all altered to produce chemicals that draw mosquitoes in, and at the same time, make you more desirable for them to bite. When they do, they have a high chance of slurping up the Gameozoites. Repeat this process across a large population, and you have millions of them accumulating in a mosquito's gut and salivary glands, where they produce their own sporozoites to begin the process again. Meanwhile, for the hosts, the infection causes all the symptoms I've mentioned before, but it also causes red blood cells that aren't destroyed to become fragile and more rigid, and thus unable to squeeze through capillaries. This means that they can start clogging up circulation in major organs, including the kidneys, the lungs, and even the brain. The results can be everything from strokes to multi-organ failure, and as a result, an early grave. And because of this long incubation time and the fact that infected humans smell delicious to mosquitoes, Plasmodium has been able to spread globally, from Africa to Asia to the Americas. Just to give you another idea, there's a wide variety of blood cell disorders that cause malformed red blood cells. Sickle cell anemia, thalassemias, epileptocytosis, Southeast Asian ovocytosis, yes, that's actually what it's called, glucose 6-phosphate dehydrogenase deficiency. One theory suggests that these weren't random mutations, but natural selection finding a way to combat Plasmodium infection. Let that sink in for a moment. This disease is so dangerous, it may have reshaped our genome. Not directly, but in the struggle to survive, it may have led to some of our ancestors developing blood disorders, some of which have their own potentially lethal problems, but nevertheless conferred enough of a survival advantage to early humans for them to pass them on to us, all in the face of one disease. So if you have any of these conditions, or know someone who does, you can blame it on the existence of this thing. So now that we know what malaria is and how it works, how have we been dealing with it? Well, Plasmodium itself wasn't identified until 1897, but treatments for malaria have existed since antiquity. The oldest of these was the cinchona tree, whose bark contains quinine. It was used as a traditional medicine among indigenous groups in Peru for centuries, and later adopted by Europeans during the 17th century. In 1820, French chemists Jean Petelier and Jean-Baptiste Caventou isolated the alkaloid from the bark and enabled its usage as the first effective anti-malarial. But while it's highly toxic to Plasmodium and inhibits its growth, quinine isn't a vaccine. It only really works as a treatment for those who are already infected. And because medical science at the time played fast and loose with ethics, once we had this, some considered other uses. One of those? Malaria therapy. This was part of a broader medical treatment in the early 20th century called pyrotherapy, where patients with untreatable diseases would be injected with an active form of a pathogen, which would cause a high fever, and the resulting spike in body temperature would reduce the symptoms or even cure the first condition. Maybe. Hopefully. And yes, this was done with malaria. In 1917, Austrian physicist Julius Wagner-Wareg attempted to cure 9 patients diagnosed with neurosyphilis by deliberately injecting them with the blood of an infected soldier. And 6 of those patients actually showed some degree of recovery. As a result, this treatment would continue in some form until penicillin was found to be more effective for the treatment of syphilis. Surprisingly, malaria therapy actually managed to cure around 50% of those who were infected, while another 15% died of the disease itself. But while it was mostly ineffective and deeply unethical, his therapy did help play a role in our understanding of how malaria works. It was also during the Second World War that a new treatment was developed, chloroquine. This had actually been manufactured in the interwar years, but after the Allies were cut off from valuable quinine stores in the Netherlands and Indonesia, this chemical was rediscovered. While it wasn't deployed soon enough to be an effective treatment during the war, it did see plenty of use in a post-war extermination campaign against malaria. Unfortunately, as we'd later see with bacteria and antibiotics, overusing a drug can easily lead to its target developing a resistance. Remember how I said malaria is caused by 5 different species of Plasmodium? One of them, Plasmodium falciparum, would go on to do just that. Dubbed CRPF, it would emerge on 4 separate landmasses between 1957 and 1983. This mistake would unfortunately go on to be repeated with two other anti-malarials, sulfadoxine pyrimethamine and methylquine. And quinine wasn't cutting it anymore as an effective treatment. This didn't make Plasmodium more dangerous or infectious, but it did make what was previously a treatable illness suddenly a lot harder to manage, especially for people in poorer rural regions where access to these medications was already difficult. So, by 1990, the war against malaria seemed like a losing battle. But, do you remember how I said anti-malarials had existed since antiquity? One of those dates back to the Han Dynasty in China. One book from 168 BC mentions a plant called qinghao, or sweet wormwood. This was recommended by that book as treatment for hemorrhoids, but another prescribed it for chills and fevers. And in 1972, Chinese researchers discovered that when feeding it to mice infected with a lethal rodent malarial strain, it was just as effective as chloroquine and quinine at clearing out Plasmodium. This is how we got artemisinin, an anti-malarial that was not only more effective and fast-acting, it was significantly more difficult for Plasmodium to tolerate. And with that came a new form of treatment called artemisinin-based combination therapies, or ACTs. Instead of a one-and-done approach, ACTs use the anti-malarial in combination with a series of partner drugs, which can be switched out and personalized depending on the patient. The goal with this is to ensure that enough of an assault on Plasmodium is carried out that it can't survive or develop a resistance. And these have proven highly effective. Even with these issues regarding resistance, between 1955 and 2025, 47 countries and one territory have eliminated malaria within their borders, completely. This year alone included Georgia, Suriname, and Timor-Leste to that list. And yes, while it remains a serious problem in 83 countries, the number of deaths caused by malaria has fallen globally. In 2004, global deaths from malaria peaked at 917,211. By 2010, that had fallen to 866,406. By 2015, 715,355. By 2019, this had all declined to just 667,648. But in 2020, due to certain circumstances, malaria deaths increased for the first time in years, reaching 747,147, which slightly increased the following year. But these were not universal increases, as Africa and Latin America actually saw fewer cases, while Asia and Oceania saw more. But even with this slight uptick, the elimination campaign proved effective in countries such as Egypt, Azerbaijan, Tajikistan, and Belize. And this uptick didn't stop momentum, as 2023 saw global deaths fall below 600,000 for the first time. Between 2020 and 2023 alone, even with the world's myriad of problems, it's estimated that around 2.2 billion cases and 12.7 million deaths were averted. But you remember how Plasmodium had developed a resistance to all those previous anti-malarials? Well, in 2015, it was found that some had developed a resistance to artemisinin as well. This strain is heavily contained, and multi-drug treatments still work, but as resistance continues to develop to established methods, we need a better long-term solution. Now, up to this point you may have wondered, why don't we just get rid of mosquitoes? If these are the vector for diseases like malaria, wouldn't we solve the issue? This isn't a new idea, and it's been considered for a long time. Initial efforts included trying to drain swamps and wetlands to prevent them from breeding, but this had severe negative side effects for everything else that needs them. Then, we decided to try using pesticides, the most famous being DDT. From the 40s to the 60s, these proved effective at controlling the spread of mosquitoes and other crop pests. And then it was discovered that these don't break down as easily as we'd hoped. Instead, DDT and other chemicals sank into the soil or into runoff water, where they were carried into streams and rivers. They would accumulate as it moved up the food chain, with effects ranging from making fish dangerous to eat to nearly driving birds like the bald eagle to extinction in the US. Meanwhile, mosquitoes and similar pests began developing resistance to the pesticides. In trying to solve the problem, we actually made things much worse. While it was banned for usage in agriculture, DDT is still deployed as an insecticide in extreme controlled methods, and only in areas with high levels of malaria. But even then, resistance remains a serious problem. So, we can't use pesticides or anti-malarials too much without the risk of them becoming ineffective. But what's the solution then? Well, in the late 80s, research began at institutes in Belgium and the United States, with the first studies carried out in 1997, followed by clinical trials between 1998 and 2012. and the preliminary results were released in 2014. These were part of the first attempt to develop a vaccine against Plasmodium, and this was found to cut infection rates for children by 50%, and in infants, 25%. The result of all this was a new plan in 2015 with a brand new tool, the RTSS vaccine, or Mosquirix. Mosquirix? I don't know how you say that. Not only was this the first true malaria vaccine, it was the first vaccine for a parasitic disease ever made. The pilot implementation took place in Malawi, Ghana, and Kenya between April and September 2019. This, combined with long-established prevention methods like mosquito nets and indoor spraying, have been a major factor in cutting death rates. But Mosquirix is only used to inoculate children, who are at a higher risk than adults. These trials led to the development of the second vaccine, R21 Matrix M. These two, combined together alongside established methods, have guaranteed that massive decline we saw in casualties after the 2020 spike. Although, as a vaccine, while it doesn't kill Plasmodium, it prevents any recurrent infections. But these are only for the most common form of Plasmodium, and going back for repeat injections annually is difficult and expensive for a lot of communities in the worst affected areas. But as for another solution, the answer might be surprisingly simple. We use that resistance to our advantage. As far back as 2007, there was the idea of modifying mosquitoes with a resistance to malaria and other pathogens. This became a reality with the creation of the transgenic mosquito, modified with a gene called PAI1. This creates proteins that inhibit the sporozoite's ability to produce a protective coating, and thus kills them off within the mosquito's body. And this has the added benefit of blocking reinfections in both mosquitoes and their hosts. The goal here is to introduce these modified mosquitoes into wild populations, allowing them to breed and pass this immunity on. The reason for all this is because, while they're a nuisance to us, mosquitoes are actually a vital pollinator most of the time. They don't even regularly consume blood. Only females do to provide nutrients for their eggs. So instead of risking another environmental cascade effect, this program aims to provide mosquitoes with their own genetic resistance against Plasmodium. If that sounds crazy, this year saw the first deployment of transgenic mosquitoes in Hawaii in an effort to save endangered birds from avian malaria. Now, while these mosquitoes are an invasive species in Hawaii, and this program's goal is to sterilize and shrink their population, this still came after years of regulatory efforts and studies done before they were ever deployed. And we could further expand this genetic resistance to our own bodies, either by targeting hemazoin or targeting aquaporin 3 as a means to curb their reproduction. The bottom line is, if it can be done here and in other places, it could prove viable for the malaria strategy as well. With these efforts and ongoing successes, the goal is to ensure that malaria is eliminated by 2040. And even if it takes longer, it can be done. 20 years ago, almost 1 million people died from this disease. Most of them were children. 20 years from now, children might only hear about malaria as part of medical history. I, for one, can't wait for that day. And speaking of medical success stories, check out this video about how one of the most famous faces on Twitch has helped save thousands of lives. And if you want more stories about how our world is getting better, check out this one here.